Welcome to the third part of this tutorial about genetic algorithms. In this part, we will be discussing crossover operators, some of their uses and benefits. So first of all, as an introduction to crossover, the crossover operator is similar to a reproduction and a biological crossover. In this one, more than one parent is selected and one or more offsprings are produced using the genetic material of the parents. Crossovers are usually applied in genetic algorithms with a high probability. It is to be noted that crossover operators are very generic, and the GA designer might choose to implement a problem-specific crossover operator as well. So let's start with the first crossovers. We've got the one-point crossover. In this one-point crossover, a random crossover point is selected and the tails of its two parents are swapped to get new offspring. The multi-point crossover. The multi-point crossover is a generalization of the one-point crossover wherein alternating segments are swapped to get new offspring. The uniform crossover. In a uniform crossover, we don't divide the chromosomes into segments. Rather, we treat each gene separately. In this, we essentially flip a coin for each chromosome to decide whether or not it will be included in the offspring. We can also bias the coin to one parent to have more genetic material in the child from that parent. The whole arithmetic recombination is commonly used for integer representations and works by taking the weighted average of the two parents by using the following formulae. Obviously, if alpha is equal to 0.5, then both the children will be identical as shown in the following image. Davis's order crossover. OX1 is used for permutation-based crossovers with the intention of transmitting information about relative ordering to the offsprings. It works as follows. First, you create two random crossover points in the parent and copy the segment between them from the first parent to the first offspring. Now, starting from the second crossover point in the second parent, copy the remaining unused numbers from the second parent to the first child, wrapping around the list. Then repeat for the second child with the parent's role reversed. Repeat the same procedure to get the second child. There exist a lot of other crossovers like partially mapped crossover, order-based crossover, shuffle crossover, ring crossover, etc. Let's talk a little bit about mutation. In simple terms, mutation may be defined as a small random tweak in the chromosome to get a new solution. It is used to maintain and introduce diversity in the genetic population and is usually applied with a low probability PM. If the probability is very high, the GA gets reduced to a random search. Mutation is the part of the GA which is related to the exploration of the search space. It has been observed that mutation is essential to the convergence of the GA, whilst crossover is not. There are various mutation operators. Let's discuss a little bit of some of the most commonly used. Again, this is not an exhaustive list, and the GA designer might find a combination of these approaches or a problem-specific mutation operator more useful. The first one is the bit flip mutation. In this bit flip mutation, we select one or more random bits and flip them. This is used for binary encoded GAs. Random resetting. Random resetting is an extension of the bit flip for the integer representation. In this, a random value from the set of permissible values is assigned to a randomly chosen gene. The swap mutation. In a swap mutation, we select two positions on the chromosome at random and interchange the values. This is common in permutation-based encodings. The scramble mutation. The scramble mutation is also popular with permutation representations. In this, from the entire chromosome, a subset of genes is chosen and their values are scrambled or shuffled randomly. The inversion mutation. In inversion mutation, we select a subset of genes like in scramble mutation, but instead of shuffling the subset, we merely invert the entire string in the subset. The survivor selection policy. determines which individuals are to be kicked out and which are to be kept in the next generation. It is crucial as it should ensure that the fitter individuals are not kicked out of the population, while at the same time diversity should be maintained in a population. Some GAs employ elitism. In simple terms, it means the current fittest member of the population is always propagated to the next generation. Therefore, under no circumstance can the fittest member of the current population be replaced. The easiest policy is to kick random members out of the population, but such an approach frequently has convergence issues. Therefore, some of these strategies are widely used. First one is age-based selection. In age-based selections, we don't have a notion of fitness. It is based on the premise that each individual is allowed in the population for a finite generation, where it is allowed to reproduce. After that, it is kicked out of the population no matter how good its fitness is. For instance, in the following example, the age is the number of generations for which the individual has been in the population. The oldest members of the population, that is P4 and P7, are kicked out of the population, and the ages of the rest of the members are incremented by 1. Then we have fitness-based selection. In this fitness-based selection, the children tend to replace the least fit individuals in the population. The selection of the least fit individuals may be done using a variation of any of the selection policies described before: the tournament selection, fitness proportionate selection, etc. For example, in the following image, the children replace the least fit individuals, P1 and P10 of the population. It is to be noted that since P1 and P9 have the same fitness value, the decision to remove which individual from the population is arbitrary. The termination condition of a genetic algorithm is important in determining when a GA run will end. It has been observed that initially, the GA progresses very fast with better solutions coming in every few iterations, but this tends to saturate in the later stages where the improvements are very small. We usually want a termination condition such that our solution is close to the optimal at the end of the run. Usually, we keep one of the following termination conditions. A, when there has been no improvement in the population for X iterations. Or B, when we reach an absolute number of generations, or C, when the objective function value has reached a certain predefined value. For example, in a genetic algorithm, we keep a counter which keeps track of the generations for which there has been no improvement in the population. Initially, we set this counter to 0. Each time we don't generate offsprings which are better than the individuals in the population, we increment the counter. However, if the fitness of any of the offsprings is better, then we reset the counter to 0. The algorithm terminates when the counter reaches a predetermined value. Like other parameters of a GA, the termination condition is also highly problem-specific, and the GA designer should try out various options to see what suits his particular or her particular problem the best. So we come to conclude this part of our tutorial. We can say that GAs are very general in nature. And we just by applying them to any optimization problems wouldn't give good results. Okay? What we want is to try and understand how a GA designer or a GA implementer can make a more successful task. First of all, it has been observed that the more problem-specific domain knowledge we incorporate into the GA, the better objective values we get. Another problem-specific information can be done by either using problem-specific crossover or mutation operators, custom representations, etc. Secondly, we need to reduce crowding. Crowding happens when a highly fit chromosome gets to reproduce a lot. And in a few generations, the entire population is filled with similar solutions having similar fitness. This reduces the diversity, which is very crucial to ensure the success of a GA. There are numerous ways to limit crowding. Some of them are mutations, switching to rank selection or tournament selection, and fitness sharing. Okay, so this is where an individual's fitness is reduced if the population already contains similar individuals. Randomization helps. It has been experimentally observed that the best solutions are driven by randomized crossovers, as they impart diversity to the population. The GA implementer or designer should be careful to keep sufficient amount of randomization and diversity in the population for best results. Hybridization of a genetic algorithm with local search. A local search refers to checking the solutions in the neighborhood of a given solution to look for better objective values. It may be sometimes useful to hybridize a GA with local search. The following image shows the various places in which local search can be introduced. For example, in the population initialization, local search after a crossover or after a mutation. In genetic algorithms, there is no one-size-fits-all or a magic formula that works for all problems. Even after the initial GA is ready, it takes a lot of time and effort to play around with the parameters like population size, mutation, crossover probability to find the ones which suit a particular problem. Genetic algorithms are primarily used in optimization problems of various kinds, but they are also used in other application areas. I'm going to give you a short list of optimization areas where these can also be used. So first of all, optimization. GAs are most commonly used in optimization problems wherein we have to maximize or minimize a given objective function value under a given set of constraints. In economics, GAs are also used to characterize various economic models like the cobweb model, game theory, equilibrium resolution, asset pricing, etc. Neural networks. GAs are also used to train neural networks, particularly recurrent neural networks. Parallelization. GAs have very good parallel capabilities and prove to be very effective means in solving certain problems and also provide a good area for research. Image processing. GAs are used for various digital image processing tasks, such as dense pixel matching. We've got vehicle routing problems with multiple serve-time windows, multiple depots, and a heterogeneous fleet. Scheduling applications. GAs are used to solve various scheduling problems as well, particularly the timetabling problem. Machine learning, as already discussed, a genetics-based machine learning is a niche area in machine learning. Robot trajectory generation. GAs have been used to plan the path which a robot arm takes by moving from one point to another. Then there's the parametric design of aircraft. They've been used to design aircrafts by varying the parameters and evolving better solutions. DNA analysis. They've been used to determine the structure of DNA using spectrometric data about the sample. Multimodal optimization. There are very good approaches for multimodal optimization in which we have to find multiple optimum conditions. And the traveling salesman problem and its applications. GAs have been used to solve the TSP, which is a well-known combinatorial problem using novel crossover and packing strategies.